Okay, this is lecture 4.2 on exponential functions. So this first little text box right here is just a reminder that if b, which is our base, is a real number, then b raised to the fractional power m divided by n is equal to the nth root of b itself raised to the mth power. So in these cases, m and n is a rational number. That means m is an integer and n is an integer. And again, remember, integers are positive or negative whole numbers plus 0. So that's kind of setting the stage of what we're going to do next. So up until this point, the exponents of a real number that we have studied have always been rational numbers, fractions. But we want to extend those exponent values beyond the rational numbers. We want to include exponents which are irrational numbers, like the square root of 2, or for that matter, pi. And in this very chapter, chapter 4, we're going to introduce to you a new irrational number. It's called, here's the name, it's a French very famous mathematician. I mispronounced it my entire life until I started taking graduate classes where I finally heard the right pronunciation. It's not Euler, but Euler. Euler's E. And that's going to be a brand new irrational number for us. It's got a lot of properties. For those of you who go on to calculus, it will be called a transcendental number, but you probably won't understand what a transcendental number is unless you are a math major and you take a class in abstract algebra. But at any rate, back to where we started. We want to define a function whose domain is all of the real numbers. And that function would be something like this. F of x is equal to some fixed number b, which is our base, raised to the exponent x. So if its domain is minus infinity to infinity, we also have to allow x to be irrational, because that domain, the real numbers, contain more than just rational numbers. Functions of this form, f of x are equal to b to the x, are called exponential functions. And they form a very important class of mathematical functions. And I don't know, we've been with COVID now since, April or something? The model for COVID-19 spread in the population is a model where it's a mathematical model, and one of the engines, it's a pretty important engine, is an exponential function. Anything that self-replicates, for example, fire. If fire has fuel, it will self-replicate and grow really, really fast. Viruses self-replicate, and they're passed from humans to humans, so they grow. The rate of growth is not as fast as, say, fire, depending on what kind of fire and what type of fuel, but they're modeled by exponential functions, in part because just like fire, it will eventually run out of fuel. Just like COVID-19, it eventually runs out of people to infect. Either it kills everyone or it doesn't, and those that it doesn't kill become immune, at least temporarily. We don't know exactly how long that will be for COVID-19. But COVID-19 is just one particular disease model. Every disease model that self-replicates is modeled on an exponential function. And we've been modeling these long before COVID-19 ever hit the scene. So let's do some experiments. So let's compare two types of functions. So remember, y is going to be f of x. So we're going to explore f of x is equal to x squared. You already should be able to picture that in your mind. That's a parabolic function. But now we're going to flip things. Let's do y is equal to 2 raised to the x. So y is equal to x squared. So there's our parabolic function, just like we've been seeing. It should be an old friend by now. And now let's do y is equal to 2 is our base, raised to the x. Now I see something. I'm going to go ahead and turn off my parabolic function. Now I see something quite a bit different. The growth of the exponential function quickly exceeds, so I'm talking about the steepness of the green line versus the steepness of the gray line. You'll notice as I go up in value, I'm only up to 138, that they get further and further apart. I'll zoom way out and go down, and you can see them getting further and further apart as I zoom in. That means that the exponential function is increasing much faster than the parabolic function, or the degree 2 polynomial. But then when we come down here, look, we notice that there is a point where they are actually the same. It's the value of 2, because 2 squared is the same as 2 squared. And then there's a little bitty space where they change. Notice where the exponential function crosses the y-axis. It crosses the y-axis when x is equal to 0 and the output value, f of x, in this case f of 0, is equal to 1. And then it looks to have a horizontal asymptote at y equals 0. It gets closer and closer. And indeed, that's the case. Let's try some other ones. Let's try a different base. Let's do y is equal to 1/2, which I'm going to enter in as 0.5, raised to the x. Now, a is actually less than 1. 0.5 raised to the x. Look what it did. I'm going to turn off this one. So compare, this is y is equal to 1/2 raised to the x. That may be rather surprising. Interesting. Look at some more things. So again, we have, in this case, looking at the green function. The green function is an increasing function. That means, by definition, the function y is equal to the x, which is the green function, as an inverse function. Now the red, the graph of y is equal to 1/2 to the x, which is the graph in red here, is a decreasing function over its entire domain. And indeed, it also has an inverse. And look right here where the y-intercept is. It's 0, f of 0, which is 0, 1. So let's go back and look at some more properties. You can experiment with y. This is for you to do. I literally give you the URL for GeoGebra. You may have something else you prefer, and you can experiment on your own. So let's look at some additional properties of exponents. So here we're restricting the base. So here's the only thing I will tell you I've done. We have talked about the base of an exponent for most of this class, and we usually call the base, or we denote the base with the letter b. For some reason, the book uses the variable a. I don't. I use the variable b, but it doesn't matter as long as you understand which variable represents the base. And here's the other thing. The base is set. It's only a variable in the sense that it's an unknown. It represents some unknown value. But once you fix it, once you decide, it doesn't change. The thing that changes in the function, the independent variable, is the x value. So a is fixed, and call it a or b. That's going to be our base. And we're going to stipulate that once you decide on it, it's going to be greater than 0, but it's not going to be equal to 1. So those two things keep in mind. Exponential functions have as their base a number which is greater than 0, but not equal to 1. So here are the properties. If these two criteria hold, here is the properties. Remember, f of x is equal to a to the x. That's f of x is equal to b to the x just by relabeling. It's a unique real number for all real numbers x. If a to the b is equal to a to the c for some numbers b and c, then that means b is equal to c. That's if and only if. That's even stronger. A to the b is equal to a to the c if and only if b is equal to c. So that tells us that the function is a one-to-one function. But we already knew that by its graph, because it's either an increasing function or a decreasing function across its entire domain, which is the real numbers. Now, notice a is greater than 0 but not equal to 1. So we have two possibilities. A can be greater than 1, or a can be between 0 and 1. It can't be 1. So we're going to consider the first possibility. If a is greater than 1 and the value of m is less than the value of n, then a to the nth power is less than a to the nth power. For example, let's let a be 2, and m be 3, and n be 5. Then 2 to the third is less than 2 to the fifth. What that tells you is when a is greater than 1, the exponential function is an increasing function. And we actually see that right here with the green value. My base is 2. 2 is clearly greater than 1. And we see that the function is increasing over its domain. Here, in our second example, which is given here, if a is between 0 and 1, and I've set a in our graph to be exactly 1/2, then the result is that we have a decreasing function over its entire domain. But notice there's some interesting things that are similar. The y-intercept is at 0, 1. If the function is increasing, then as the values of x get smaller and smaller, get more and more negative, approach minus infinity, then the value of y approaches 0. If a is between 0 and 1, as the value of x increases, then the value of f of x decreases to the asymptote y is equal to 0. So here is the definition of the exponential function. Let b be greater than 0 but not equal to 1. Then the exponential function to the base b, again I've changed the base to be b, it's easier to remember, is defined to be f of x is equal to b to the x. So here's some mathematical reasoning. This has a high chance of being on your next exam. Use the additional properties of exponents. So all of our properties of exponents hold, together with what we learned in section 4.1, to give reasons why exponential functions are one-to-one functions. Well, that's literally already answered to you if you've been listening carefully to this lecture. What happens if we allow b to be equal to 1? Would it be a one-to-one function? And that's the part you need to answer on your own. So let's do these particular problems. So f of x, so this is example 1a. So f of x is equal to 2 to the x. So let's find the value of f of minus 1. Well, that's just 2 raised to the minus 1 power, but I can change that exponent, which is negative, positive exponent, by moving the 2 across the division line. And of course, since the exponent is 1, it's just equal to 1/2. And here again, this is the answer I want to see. In these cases, this is a particular area of the book where you do get to use your calculator, but just don't whip out a calculator and put in 2 raised to the minus 1 and report 0.5. That's lazy, in my view. And it shows that you're not confident in mathematical skills, because computing that is pretty simple. So let's do 1b. I say it's lazy, not the person who does it is lazy. So what's f of 3? Well, f of 3 is 2 to the third, which by definition is 2 times 2 times 2. It's our base multiplied by itself 3 times, which is 8. And over here we'll do 1c. What's f of 5/3? No, there we go. That's equal to 2 raised to 5/3, which is equal to the third root of 2 raised to the 5th power. And that's where you stop. That's where I want to see. That answer is exact. Now, I know you could plug this value into your calculator to find out what it is, but that's not what we want. We want exact solutions when we can get them. And that's where you stop right there, is just the third root of 2, which is an irrational number, raised to the 5th power. And I'm not even going to show you how to do that on your calculator. Not yet. When your calculator skills are needed, which they will be eventually, I'll show you how to do things with the calculator. So let's just look at, actually, I'm going to snip out this whole thing. I want to be able to write. Flame shot. Take screenshot. So here we go. So let's do these one by one. So we're given a function f of x is equal to b to the x. What is the value of f of 0? Well, f of 0 is equal to b to the 0th. And what do we know about b? We know that b is greater than 0 and that b is not equal to 1. So since b is not equal to 0, this is easy peasy. It's equal to 1. So that means 0, f of 0. So you should know abstractly that that is the y-intercept point, is equal to 0, 1. Isn't that a nice answer? All of our exponential functions have the exact same y-intercept. All of them do. They all intercept the graph on the y-axis at the point 0, 1. And this answers our next question. What is the y-intercept? Well, we just discovered it. It's 0, 1. When x is equal to 1, what is the value of f of x? Well, f of 1 is equal to b raised to the first value, which is equal to b. So that means the point 1 and b, where b is a fixed base value, which we would know, also lies on the graph. So I have 2 points that lie on the graph. When x is equal to -1, what is the value of f of x? So f of -1 is equal to b to the -1, which is 1 over b. So that gives us another point that lies on the graph, -1 and 1 over b. So we already have 3 points that lie on the graph of every exponential function. Now the point 0, 1 is common for all of them. The point 1, comma b, well, that's going to vary depending what your actual given value of your base is. And -1, 1 over b, that will also depend on what the value of your base b is. What happens to f of x is x goes to -infinity. So that's going to be an interesting question. What happens to x? What happens to f of x, sorry, as x goes to -infinity? So let's come over here and answer that in 2 parts. So let's give an example. Let's suppose b is greater than 1. So let's just look at a paradigm case. Let's say b is equal to 2. And our function then is going to be f of x is equal to 2 to the x. So let's plot some values. So 0, -1, -2, -10, -100. Well, f of x is equal to 2 to the x. And we're questioning what happens as x goes to -infinity. And this is really just a small little bitty bit down that road, but we're going to see a pattern. So 2 to the 0th is equal to 1. 2 to the -1 is 1/2. 2 to the -2 is 1/4. That's smaller than 1/2. 2 to the -10 is 1 over 2 to the 10th, which is equal to 2, 4, 8, 16, 32, 64, 128, 256, 512, 1 over 1028, which is even smaller. So we can see in the case when b is greater than 0, as x goes to -infinity, f of x goes to 0. So let's do the other case. Suppose b is between 1 and 0. For example, our paradigm case will be f of x is equal to 1/2 raised to the x. Well, let's see what happens as x goes to -infinity. So again, we'll just make a few values here because we already know it's an increasing or a decreasing function. So all we really have to do is find out whether it's increasing or decreasing. And if it's decreasing, it'll continue to decrease. If it's increasing, it'll continue to increase. In this case, as, let's kind of sketch the graph here, as x goes to minus infinity, it decreases. So here, that's when b, in this case here, that's when b is greater than 1. And now we're doing the second case. I guess I could put some kind of divider there. Our second case is when b is between 0 and 1. Same question. What happens when b goes to minus infinity? So let's make a table of values for our x. And the really important thing here with exponential functions is that we consider negative values. Let's just do these two. 1/2 to the x. So that's going to be 1. But what is 1/2 raised to the minus 1? Well, using our exponent rules, that's 1 raised to the minus 1 over 2 raised to the minus 1. Well, 1 raised to the minus 1 is 1 over 1, which is 1. And 2 raised to the minus 1 is 2 over 1. So that's 2. So let's do 1/2 raised to the minus 2. Well, that's going to be 1 over 2 raised to the minus 2, which is the same as 2 raised to the 2 over 1, which is 4. So we see that f of x increases. So our sketch might be something like this. So it increases rather than decreases as x goes. So it's got to go this way. Because as x goes to minus infinity, which is heading down this way, our function value is increasing. And here is a quick question for both of you, for all of you. What is that point right there? And what is that point right there? If you're awake and still following this, you'll know it's 0, 1. And you should know that that is 0, 1. So we had multiple answers to this question. Depends on the value of our base. So if our base is greater than 1, it decreases. If it's less than 1 but greater than 0, it increases. So what does your answer to E tell you about the existence of a horizontal asymptote for f of x? It's always y is equal to 0. It tells you the line, so I'm going to do it, tells you the line y is equal to 0 is the asymptote for the basic exponential function. And by the basic exponential function, I mean that right there. Clearly, you can, I'm hoping you can imagine, we can add constants to it. That's going to raise it up or shift it down vertically. And we can do things with the x value, such as b to the x minus 3. And all of the stuff that we learned earlier on how that affects the graph still is in play. What is the equation for the horizontal asymptote? I wrote it down for you right here. That's the equation. What is the domain? The domain is minus infinity to infinity, the same as a polynomial. What seems to be the range? So by its graph, the range, the only thing really to ask here is whether 0 is included, and it's not, is 0 to infinity. And how do we figure that out? Range is always difficult. We figured that out by the graph. By the graph, it's either going to be 0 to infinity, where 0 is included in the set, or excluded in the set, and it's actually excluded. And that's literally the question I'm asking here. Does it ever cross or touch, I should put in there touch as well, its horizontal asymptote? And the answer is no, again, by the graph. But that's really hard, right? That's not a really good answer, because I can never see what goes on at minus infinity. No matter how negative the value is, there's more values that are more negative. So maybe if I go out to minus 10 to the 100 millionth, which is an extremely, extremely large negative number, and it doesn't cross the y-axis, the x-axis, I could still go further out. Maybe it did. So this is kind of a hand-wavy answer. It turns out that it's true, but it's a hand-wavy answer. And the answer as to why it's true, actually, we get from analysis. And I think that we can find it via algebraic means as well. And if that's the case, I'll put yet another extra credit up for you so you can explore that question. The exploration will be guided by me. How is that? I know I did it last semester during the COVID break, but suddenly I was stuck at home too when I wasn't stuck at being at home, and I had a lot of free time. So here we already figured this out. Here they're using the variable a. I use the variable b because b stands for base. So we literally figured out all of this, and by the range, this is the actual answer, but knowing what it is, and knowing that that's actually the case, you have to more or less accept it on faith at this point, because the graph can't tell you. So let's use and do this next exercise. So use the above information in a table of values that includes values of x in the set 2, minus 1, 0, 1, 2 to graph this. So again, I want to grab this. Won't grab the whole thing, I'll just grab part of it. Bear with me, I think I accidentally started another instance of well, maybe not. Seems to be locking up on me. See what it's doing there? See if I can close it. Yeah, let's just quit. I hit the wrong icon, and I think another instance was trying to open up. And this is Linux, and it's a great operating system. Love it. I'll never go back to Windows. But it's still got some bugs here and there, and that happens to be one of them with this particular program. It may very well be the program is buggy and Linux is fine. So our function is f of x is equal to, notice my base is 1/5 to the x. So from what we said before, we know that this is, as x gets smaller and smaller, larger and larger in negative value. So it means as x approaches minus infinity. So sometimes the use small can be ambiguous. Usually we try to restrict small in mathematics to mean numbers which are less than 0. that approach 0. Numbers which are like -5, that's a negative value. Those aren't small, those are just numbers that are getting larger and larger in negative value. So, excuse me if I misspoke there. So this is going to be my x, and this is going to be my 1/5 to the x. So the thing is, I ask you just to find these values right here. So we just have a set of 5 values. And the cool thing about this is that the first thing we're going to do is we're going to identify the value of b. This is b to the x. So b is equal to 1/5. So the first thing we know is when x is equal to 0, I'll go 0, 1, 2, and then do -1 and -2. They don't have to be in order. They're just points, okay? So I already know that the value when x is equal to 0 is 1. So I can immediately put this point right there. That's the value, because this is another name for the y-intercept. Now, what about x is equal to 1? Well, when x is equal to 1, what did we discover? The point 1 and b is on the graph, and -1 and 1 over b. So b is equal to 1/5, so that means 1 corresponds to 1/5, and in our case, -1, and 1 divided by 1/5 is 5. So I don't have to do any work for this answer right here, besides erase what I tried to write and write the correct thing. I was going to write a point there, but we just want the value. So the value is 1/5, and the value down here is 5. So the only thing we have to do is evaluate f of 2, which is 1/5 squared, which is 1 squared over 5 squared. But 1 squared is 1, and 5 squared is 25. So that's 1 over 25. And f of -2 is 1/5 raised to the -2 power, which is 1 raised to any power is 1. 1 over 5 to the -2, which is 5 squared, which is 25. So let's plot these the best that we can. I've already plotted 0, 1. So 1 and 1/5, it's really, really close. And then 2 and -1/25, it's even closer. Then, sorry, I just did those wrong. 1 and 1/5 is there, and 2 and -1/5 is right there. -1 and 5. -2 and 25. So you can see it's going to be a function that looks something like that. I won't try to draw anymore. If you want to see exactly what it looks like, go to GeoGebra. But we already know it's a decreasing function because b is between 0 and 1. Specifically, it's 1/5. So here we go. We have exponential functions. That means there is such a thing as exponential equations. So what are those exponential equations like? So let's read through this really carefully. Let w be a degree 1 polynomial in the variable x. So degree 1. For example, w minus 3x or 5x plus 7. Another word for a degree 1 polynomial is a linear polynomial. And let c and b both be greater than 0, with b, which is going to be our base, won't be equal to 1. Then c is equal to b raised to the w is an exponential equation. So remember, we're restricting right now for you guys that our exponent w is just a degree 1 polynomial. And clearly, if w is just equal to x, x is the simplest degree 1 polynomial we can get. So here is an example of such a polynomial equation. So let's make sure we understand that. So here's our paradigm. C, better, much better. So we have C is equal to b to the w. W is a linear, I like that easier because it's that easier to write, linear polynomial in the variable x. What is c? C and b is the base, and c is a fixed constant. That's the reason it is c. Then c is equal to b to the w is a polynomial equation that we want to solve. Notice c is a constant. It's a given constant. So we're given down here 81 is equal to 1/3 raised to the x. But notice I did not give it to you that way. It's given to us in the book reversed around. So w is the polynomial x. It's a linear polynomial. I just flipped things around because this is an equality. I can move the 81 and the 1/3 across. It doesn't make any difference. So in this case, c is equal to 81. B is equal to 1/3. And just our w is equal to x. So how are we going to solve that polynomial equation? Well, here's some important information. Since exponential functions are one-to-one functions, we know that if for some values s and r, if f of s is equal to f of r, then we have to have s is equal to r. And if s is equal to r, that implies if b raised to the value of x, s, is equal to b raised to the value of r, then we have to have s. We have to have s is equal to r. So what we're going to do here is I'm going to write 81. I'm going to do a little bit of manipulation here. The first thing I'm going to do is 81 is going to stay the same. And this is the same using exponents rules is 1 raised to the x over 3 raised to the x. But that's the same since we have 1 to the x is equal to 1 for all x, that's the same as saying I have 81 is equal to 1 over 3 to the x. But I'm going to note that 81 is equal to 9 squared. And that 9 is equal to 3 squared. So 81 is equal to 9. I'm going to replace by 3 squared. So 81 is equal to 3 to the 4th. So that's information. So why did I look for 3 there? Because 3 is our base. So I'm going to rewrite what I have here using exponent rules. 1 over 3 to the x is the same as 3 to the minus x. Are you with me? Now the next thing I'm going to do is I'm going to replace 81 is 3 to the 4th is equal to 3 to the minus x. So by the one-to-one nature, this implies that 4 is equal to minus x. In other words, minus 4 is equal to x. And we have solved the equation. So take a deep breath. It wasn't so bad, was it? It wasn't so bad. So the things that we want to go back and note is, well, what is the numerical base that really does the work here? It's not 1/3, but rather actually 3, because this is another way, by rewriting just the right-hand side, 1 to the x is equal to 1. So really, the engine that drives things is 3 to the x. It's the base 3. But 1 over 3 to the x, using exponent rules again, is just 3 to the minus x. So once I've done that, I have to try to convert 81 into 3 to some power r. Maybe r is not good. Some power k. That just didn't look like a letter there. Now I have to find k, and I found k was equal to 4, because 81 is 9 squared, but 9 itself is 3 squared. So 81 is 3 squared squared, which again, using exponent rules, gave me my 81 is equal to 3 to the 4th. Then I just replace by this line right here, and then I use the fact, since these are 1-to-the-1 functions, if f to the b is equal to f to the c, then c is equal to b. So we have f to the 4 is equal to f to the minus x. That implies 4 is equal to minus x, which means minus 4 is equal to x. Okay, I'm actually going to break this lecture up into 2 parts. It's a really kind of a long lecture, and we're going to do example 5 and example 6, and then part 2 we're going to look at some compound interest problems. So I think this will be a good place to pause. So again, I just want my whiteboard here, blackboard, blue board. So we have 2 to the x plus 4 is equal to 8 to the x minus 6. Now 2 is less than 8, so what I would like to do is I would like to express the right-hand side as a power of 2. So I will note that 8 is equal to 2 cubed. So that's exactly what I'm going to do here. So 2 to the x plus 4 is equal to 2 cubed. That's my base, because 8 is my base, raised to the x minus 6. But remember our exponent rule that says a raised to the mth power raised to the nth power is equal to a raised to the m times n. So 2 to the third raised to the power of x minus 6 is equal to 3 times x minus 6, which is equal to 3x minus 18. So that's going to give me 2 to the x plus 4 is equal to 2 raised to what I did over here, 3x minus 18. So now I have the same bases, and I can use the one-to-one nature of my equation of my function to declare x plus 4 is equal to 3x minus 18. And to solve that, I'm going to bring the 18 over and go 18 plus 4 is equal to 3x minus x. 18 plus 4 is 22. And 3x minus x is 2x. So I'm going to divide both sides by 2 to get x is equal to 11. Not so bad, right? At first you see something like that, you say, I have no idea how I would solve that one. Well, that's how you solve it. Now here we have something that is similar, but there is no x in it. We want to solve this equation. There is no x in the exponent, but rather there's an x as the base. So that's the difference. The x is not in my exponent. The x is in my base. So how are we going to rewrite x to the 4/3? Well, that's equal to, we have two options. I'm going to talk about two options. That's the same thing as x to the 4th raised to the 1/3. Or we have another option, x to the 1/3 times raised to the 4th. Both of those are our options. Why is that equal to x to the 4/3? Because 4 times 1/3 is the same as 1/3 times 4. That follows from that exponential rule that I just mentioned right here. This one right here. Power of a product rule is what I think that is. So let's kind of leave this over here, and let's see what we can do with 81. We discovered that 81 in a previous problem was 3 to the 4th power. So that suggests that I want to choose this right here expression, x to the 1/3 to the 4th is equal to 3 to the 4th. So now let's do something else. Let's do a variable. Let's say, let's let w equal to x to to the 1/3. So we're going to rewrite this as w to the 4th is equal to 3 to the 4th. That implies w is equal to 3. But since our exponent is even, 4, that means plus or minus w is equal to 3. Why? Remember, 2 to the 4th is the same as minus 2 to the 4th. So plus or minus w is equal to 3. So that tells me, what is w? Plus or minus x to the 1/3 is equal to 3. And I'm going to move the plus or minus across. Let me get some more space here. So all I did is I've replaced my plus or minus w with x to the my 1/3. So now what I'm going to do is I'm going to go ahead and break this down. That means plus x to the 1/3 is equal to 3, or minus x to the 1/3 is equal to 3. But this is the same thing if I multiply both sides by a minus. Is saying x to the 1/3 is equal to minus 3. So how do I solve for x? I raise both sides to the 3rd power. So x to the 1/3 raised to the 3rd gives me x, and x is equal to 3 to the 3rd power, which is 27. So over here, we're going to do the same thing. X to the 1/3 raised to the 3rd power is equal to minus 3 raised to the 3rd power, which is equal to minus 27. So all of that tells us that x is equal to plus or minus 27. So this is an interesting problem. So when the exponent is in the base and you convert it to something raised to an even power, w to the 4th is raised to 3 to the 4th, that implies w plus or minus w is equal to 3. You have to, when the exponent is even, and you have w to the 2n is equal to x to the 1 over k. That's not helping you out. Just remember, if the exponent is even, at some step, you have to remember this over here, that we get 2 solutions. If the exponent were odd, we'd only get 1. But when the exponent is even, just as we show right here, that we have 2 possible bases. So 2 to the 4th, which is 16, is also equal to minus 2 to the 4th. And remember, we're solving for the base here, and that's the reason I have to consider the plus, and the minus base value. So this only applies when the unknown is the base. So that's going to be the end of part 1. Part 2 won't be near as long.